Hello and welcome. Thanks for listening in to my vision for formal. Very excited to share that with you. So, what is the vision going to be for formal verification in 7 years' time, in 2025? And why is that year going to be special for formal? So, I'm going to be talking about all of that. And as I said, thank you very much for listening in. So, let's take a step back. And every time we talk about vision, I want to always think about where we came from, what our heritage is, and in this case, what is the heritage of formal verification. And although the heritage is quite long, but there are key defining moments in the history of formal. And I could go back in time and think of the time of Dijkstra in 70s when he famously coined the phrase program testing can be used to show the presence of bugs, but never to show their absence. I certainly believe that this was the most important statement of the previous century. Now, Dijkstra was a very famous computer scientist who did a lot of work not only in algorithms but also in formal. In the context of formal, he said quite a few interesting things in one of the many manuscripts he wrote. And some that caught my attention was that programs should be correct, that we must prove the correctness of programs. That we must tailor our programs to the proof requirements, that programming will become more and more an activity of mathematical nature. So you can see that Dijkstra was already hinting in 70s that program testing was inadequate and we needed to go beyond testing to think about formulating proofs. And although a lot of what he was saying was in the context of software and not necessarily hardware, but what has happened is that the adoption of formal has taken off for hardware a lot more than it has taken off for software. But one thing that did not change then and still is true for formal verification in general is that there is a notion of mathematical proof, which is at the cornerstone of formal methods. That hasn't changed. Now, if you look at the triumvirate of formal technologies, it's actually a combination of three very interesting bits of technologies. We call them theorem proving, we call them equivalence checking, and model checking. And this diagram loosely illustrates the extent to which these technologies have been adopted in industry today, especially for hardware verification. So let's look at theorem provers. Theorem provers are actually machines that build proofs. They build proofs by actually applying inference rules and using automatic programs that are called decision procedures. They are powerful tools. They have no capacity limits, but no bug finding either. And training can be a bit of a challenge. So that's something I must admit, having learned two big theorem provers in the past, it can be a little daunting at first to learn these. However, there is an illustrious history of formal which is on the back of theorem provers. And actually, if you look at this slide, the very first computer-generated proof came out in 1950s by Martin Davis. And then the Stanford Pascal verifier came in 60s. Boyer-Moore's ACL2, as we all know, is one of the most well-known theorem provers. And Stanford LCF was invented by Robin Milner. Sir Milner invented this in Stanford, and then it spawned a whole family of LCF-style theorem provers pioneered by Mike Gordon and Tom Helm. And there's a whole history of Hall theorem proving dating back from Hall 88 to Hall 4, then John Harrison's Hall Light, and then Larry Paulson's Isabel, Hewitt's Cock, and Schenker and Rushby's PBS. So, there's no dearth of theorem proving, and there is no dearth of application of theorem proving. So we went from the first computer-generated proof in 1950s to actually verifying big, complex, out-of-order microprocessors, to compilers, to operating systems. So here we are in 2018, nearly 68 years, with an illustrious history of formal built on top of theorem proving. There's a fascinating book by Frank Weick that covers the 17 provers of the world. We have come a long way, no doubt. But the user base for theorem proving applications and the number of people who are able to drive them to get the work done is still quite small compared to the number of people who are trying to use tools for hardware verification. Let's take a look at another class of tools which are called model checkers. These are actually bug hunting machines that build not only proofs, but they're also able to build find bugs, and they're actually very good bug hunting machines. The way they actually build proofs is through exhaustive state space search. So there's no inference rules and not necessarily decision procedures and so on flying around. It's effectively a whole lot of state space traversal, resulting in concluding whether there was or wasn't a proof. These are again powerful tools, easy to learn, much easier than theorem provers, I have to admit, and great for debugging, for counterexamples, but unfortunately they also suffer from capacity limits. The history of model checking is also quite prolific, and it dates back to 1970s. I can think of the early work done by Amir Puneli and Leslie Lamport and Susan Novicki in 1970s when they were working on temporal specification languages inspired by philosophical logic and modal logic. So they invented a bunch of languages, the most prominent of which are LTL, linear time temporal logic, and CTL, computational tree logic. Now, while these guys were inventing languages for specification, for being able to capture requirements over time, Ed Clark's team in CMU and Joseph Sifakas' team in France were independently looking at automating model checking or state space checking algorithms. And almost at the same time, they both independently invented tools that we now know as model checkers. At the time, in 1982, they could verify systems as big as 10 to the power 20 states, and it was considered to be a massive feat. However, things did not scale very well because of explicit state space traversal, and Ken McMillan, a graduate student at CMU at the time, got inspired by Randy Bryant's BDD invention happening in the electrical engineering department in CMU, and Ken came up with an idea of doing model checking completely symbolically using BDDs. That changed the game for model checking from 10 to the power 20 states to 10 to the power 100 states. It's quite a big leap if you think of it. Lots and lots of model checkers started to emerge. Ken implemented SMB. Leslie Lamport was implementing a TLA plus language for specification and verification, also a tool. Spin was invented. Murphy was invented. A combination of tools were emerging, and there was some vigorous research going on in the field between 80s and 90s. That led to what we now know as quite a lot of advanced research and also tool support in things like bounded model checking, probabilistic model checking, event-based. You've got the EBMC tool from Daniel Kroening. You've got Martha Kowalska's PRISM tool, Rodin tool, that is for event-based programming and verification. And although all of this was actually quite exciting, but this was actually not necessarily changing the game until an event happened in 1995. Intel had a floating point bug in their divider, and that not only cost them bad publicity and a lot of money, but it was an eye-opening moment from my point of view. And Intel then invested heavily in building formal tools and technology, and they invented a whole new model checking algorithm called symbolic trajectory evaluation, pioneered by Carl Seeger and Randy Bryant. And they designed a tool called Forte, which was largely used in Intel to verify a whole generation of Pentium processors, floating point units. Forte was also available in the academic domain for some time, but I think it's no longer available now. What has happened from 2005 onwards is a lot more commercial play in the formal verification space. So we currently have now 4 big companies investing heavily in tool development, and we now have a great deal of formal adoption. But actually, I have to admit that the game kind of changed since IC3 was invented by Aaron Bradley. And I think in some ways, looking at how scalable the technology of proof convergence has become in the last decade, I can think of IC3 as a defining moment. And for some reason, I don't think IC3 gets that much credit, but almost all the major tool vendors in the market now have proof engines that have variants of IC3 flavors. So it's a thriving field, but all along when model checking was being researched and tools were being developed, in parallel a lot of research work was done in abstraction, in BDDs, in and inverted graphs, in SAT solvers, induction-based techniques, SMT solvers, and it's not like this research was done in an independent way to this. They were kind of feeding into each other, and that was the fun of all of this. So now we have like dozens of model checkers, freely available, commercial model checkers, big 4 EDA players, nearly $100 million+ industry. And today you can find applications of model checking in all sorts of complex problems, from cache coherency, from the days of Murphy, from what I can remember, CPU verification, you can have load store units, you can have data path units, memory management units, hazarding units, you can verify them today with formal GPU, video, networking, lots of packet-based designs, routers within the reach of formal today. Bus bridges, SoCs, you name it. There is no dearth of applications today. Useful reference for those of you who are interested in finding out a lot more about the foundational principles of model checking. It's a nice handbook that has been released this year by Ed Clark. The third class of formal technology, which I have to point out, is also playing a very important part today in hardware verification in industry, is equivalence checking. Equivalence checkers are actually tools that are not only just bug hunting machines, but they also are able to establish full exhaustive proofs. And they do this rather interestingly by comparing 2 models. And it's not the case that you make just 2 copies of the design and try and prove them equivalent. You may want to do this for some reason, but actually the comparisons are usually done at different levels of abstraction. So one model would be an RTL in VHDL Verilog, the other copy would be a netlist, could be an EDIF, for example. So they're again powerful technology. It can have capacity limits, but debug and learning is easy. Debugging is not that hard. So equivalence checking is well known for synthesis verification. That's where the genesis is. A lot of the work done was in IBM in the early days. And at the core of EC, we have 2 different ways of solving it. One is combinational, when you have identical state encoding, and one is sequential, where you have a very different state encoding. So both applications are useful, but sequential equivalence checking is not only a lot more useful, but also a lot harder to converge. It's a lot harder to converge for systems where you have 2 different state encodings for the models. Most sequential EC in practice is conditional, though you don't want to actually just say that the 2 models are always equal, but you might want to say that the 2 models are equal because there has been a clock gating transformation between one model to the other, and therefore I only want to observe the equivalence of these 2 models under a certain condition. And that's what is sequential in equivalence checking. And clock gating verification is a classic example of this. Other cool, scalable examples of equivalence checking are in arithmetic verification, in FPGA synthesis verification. So there's a lot of traction and work done in this. Over half a dozen players building EC tools today. However, model checking actually is a dominant force in formal, and it is the reason why formal is most widely adopted for formal hardware verification. So if I'm now to tell you what my vision is, so the vision of Axiomise and my vision is to enable formal to be used by all design and verification engineers. And I want this to be done for the right reasons and at the right time. And I think this is a great opportunity for our industry to do this. By 2025, we would be 75 years since the first computer-generated proof, and I think we are well within the reach of achieving this vision by that time. In order to understand where I'm coming from and how I'm able to see this, I see this as an interaction of three different players. One is the user who uses the tool. One is the tool technology, the EDA guys or the guys who are building tools. Some of them are freely available, for example. But also there's a massive role of methodology in actually shaping up how these tools and technologies could be used in a scalable way by the user. So there are actually three different competing forces, and to get the best out of them, you have to get the equilibrium right. If you imagine a typical commercial model checking tool from any of the four big EDA players, this kind of architecture that I have on the slide is an abstract view of looking at these tools. So they usually have compilers, they have proof engines that are able to compute full proofs or find bugs. Then you have debuggers that allow you to debug failures. And then you have some way of encapsulating how well the verification was done through some coverage calculation. And at the top of all of these, you have interactive front end. But that's not all to the tools. What you really have at the top is a layer of different apps. So at one level, you have common apps, which require very little user interaction and are largely automated. Then you have specialized apps, which are very much domain specific and require some domain knowledge, require a lot more setup, so less amenable to automation. And at the very top of this pyramid is model checking, also known as property checking or assertion-based verification. And as you can see, that the level of automation required to play successfully with this is a lot more. So actually you can't actually get a lot out of model checking just plainly through automation. So the users have to write properties, they have to model constraints, they have to write the cover properties. So it's a very much interactive activity here. Now, what you will notice is that actually if you go from common apps to the assertion-based verification layer, the number of users are decreasing, right? Kind of makes sense because this layer requires a lot more user interaction, this requires less, so you can have more people who are not necessarily very skilled or trained and they can drive these common apps, and this requires more awareness, know-how, or more resource intensive, so less people are able to do this. Kind of makes logical sense, doesn't it? But if you actually look at the amount of bugs and the quality of bugs that are found at this layer, you will often see in many projects that the assertion-based verification tends to find the most high-quality bugs and find a lot more of them. And this is the irony, that even though you have fewer users in this layer, they are giving and producing better ROI. However, what you will also see is going from common apps to assertion-based verification, there is an increased dependence on good methodologies. And better methodologies are needed as you become more and more specialized in your use of formal. This in turn has an impact, or let's say this in turn is driven from the skill level of the people who are actually driving it. So the users require very basic knowledge to set up the common apps, require a little bit of expertise to handle the specialized apps, but you require a significant amount of bootstrapping and training and acquaintance and workshop style training to get people to become experts at driving assertion-based verification. So actually, scalable formal verification methodology is what is actually required to get more users using model checking or assertion-based verification. And I would like to say that it is important because once you have more users, you will find even more bugs, and there is a better ROI proposition for formal. So why methodology, right? So as I said, without the good methodology, you have fewer users using ABV anyways. But actually, if you take a step back from verification and formal, in general, if you haven't got a good methodology, then technology is limited. And you can go back to as far back in time as Stone Age. We had stones and all kinds of tools that we were trying to discover. But if you didn't know how to use them properly, these tools meant nothing. On the other hand, you could have a lot of different principles of combining things, but you haven't got anything to combine. If you haven't got good technology, then all of these principles are just theory. So it's not that only you need one, you need both to come along. However, methodology has been the missing ingredient so far, and largely that is the reason why less people actually use formal. So let's take a snapshot, right? So from going from past to present, right, there has been a rapid growth in formal tools and technologies, certainly an increase in user space for formal tools. The user demographics have certainly changed. You don't need a PhD to drive model checking tools. But formal is not yet mainstream, and you still have to persuade your management to use formal. That's largely true in most companies. Question I have is, do we even need more formal adoption, and why? So my answer is yes, we need more formal adoption, and I'll tell you why. If you look at a typical SoC architecture, massively abstracted of course here, complexity is everywhere. You take a look at any one of these IP blocks to the north of the fabric, or any of these IP blocks, every single IP block here is big, complex, and has to be designed in time and has to be correct. So not only are these IP components more complex to design, but the verification is getting harder and harder. So for example, if you take a look at a typical design abstraction layer going from architecture to silicon, we are in an area of shrinking time to market. But shrinking time to market has not made our life hard enough if you throw in increasing verification concerns. So on the one hand, we had to only do functional verification in 90s, and performance was the only big thing. Then power, performance, and area became the next big thing because of mobile computing, right? Now you have machine learning designs. They have now come up with a new set of requirements for hardware, which makes the life even more interesting for verification. Think of instruction set architecture verification at the architecture layer. I can think of isoformal work done by ARM last year as a spectacular event in this area. Multi-threading verification, coherency, security. How big is security? Very big. Just look at Meltdown and Spectre and the whole chain of bugs that are appearing in hardware this year. Safety, compliance with ISO 26262, arithmetic verification for machine learning. All of these are important verification concerns. We try and address them at the architecture level, but actually we also keep track of these concerns and even more micro-architectural constraints like arbitration, verification, serialization, pipelining, hazarding, deadlocks, live locks. And all of this becomes important when we start building designs at the micro-architecture level. And hoping that we've actually found a lot of these bugs, we now have to not find them when we go down at the netlist level, and hopefully we can focus on synthesis correctness, clocks, resets, and power, performance, and area. And at the silicon level, on the PPA and security and safety. So it's not that the concerns are decreasing, but what's actually happening is that actually there is a diamond effect. You tend to find fewer bugs here, then you try and find more bugs at this level because you've introduced more bugs by writing design, introducing code, and then you hopefully flush them out by the time you reach the netlist layer. You tend to have fewer, and then even fewer at the silicon level. You really don't want to actually have last minute bugs. So there is a little diamond effect. But what we are really trying to achieve is to have as many bugs found at this level, so we tend to find less and less. So if I want to now realize my vision against the backdrop of shrinking time to market and in increasing verification concerns, how can I realize my vision? The way to look at this is to address the three key players: the technology, the methodology, and the users. So here is how I see technology can help realize my vision. So I see that actually there are these following challenges today in the technology space. Proof engines. They are good, They're very good at finding bugs. Some of them are great at finding proofs, but a lot of work has to be done in building word level proofs. I have a whole range of experience in working with problems where I find that not having good word level solvers is causing an exponential performance issue. I haven't yet seen a lot of SMT solvers in use, but to be honest, this needs to actually become better. This would make the arithmetic verification a lot better. Also, if you think of it from a word level point of view and word level SMT, this is going to make a big difference. We need solvers to become more domain specific. So we have way too much general purpose solvers. So we have, hardware tends to be, you can come up with patterns in hardware, right? So we can come up with patterns of solvers that we can quickly adapt to the specific kind of hardware. What we really need is a next generation of IC3, IC3++. Our compilers and elaborators have become better. We are able to swallow bigger designs. We're able to parse them, but still we can't just take the next generation SoC completely and compile it and elaborate this in good enough time. So we might have to think of a different tag here. We might have to think of customized scripts and flows to make it faster. Coverage and sign-off is a big hassle for the user community, and the technology guys have to really get their act together. The EDA guys need to come up with a unified coverage model. There are too many different ideas flying around: proof core, cone of influence, mutation-based stuff. I think all of them are good, but we need a unified coverage model, and we need this to work between different tools. We have verification planners. We have some vendors offering it. Some vendors don't have anything, and they're not interoperable. Your verification plan in one tool can't just simply load in another tool. We need to become better at that. Debuggers are still quite old. They're still quite old school. They lack intelligence. They've become better, some of them not. But what I'm lacking here is an Alexa, Amazon's Alexa or Apple's Siri type feature where I just sit back and say, hey, tell me why this property is failed. And the tool is able to infer out all of this analysis and explain to me and say, hey, go and look at these two signals. They are the ones that are actually causing this flop to have this value at this cycle, and therefore this final property has failed. Better root cause analysis, better intelligence, speech recognition, pattern matching. This is an exciting field of work that has to be done. And this is going to make Formal a lot better to use, especially debug, because it costs a lot of time. Requirements validation, we have almost nothing in the validation space. If you want to think of compliance for safety, or you want to think of validation holes for security, how are you going to do this? So we have a lot of good work done in the field of automotive for software development. I'm aware of a lot of different tools in that space, but I don't think there is anything in the hardware verification space. If we can make these technology improvements, it will get more users excited about Formal. Let's take a look at what users can do. So currently the use model is kind of ad hoc and it's kind of at extremities. So you on the one end, people use it for Formal tools for just apps, or you have gurus in some companies where they actually use it for deep Formal, as they call it, trying to do end-to-end Formal. But there isn't a full continuum, and often people don't start early enough, and if they do, they just stop it after a while. There isn't any continuity. So what we need to do is to start early, have an agile flow where we do design bring up, where we do verification using cover properties, constraints, and assertions. We then have a way to compute coverage, so we find out how good we are. If we find any holes, we are able to wrap it back to the design, and we continue this process through the life cycle of the design. And the use model has to be a lot more systematic. The training is a real challenge, as you may appreciate. Methodology training is completely missing. At Axiomise, this is what we specialize in, and we can certainly help you get better at that. Management often is not fully aware about what to expect from a typical Formal verification project. Should you be expecting bugs, or should you be expecting a coverage? Should it look like the coverage should look like this, or is it functional coverage or code coverage? What is mutation coverage to a manager? What is a proof core coverage to a manager, setting 2 levels of management up from you? What does cone of influence coverage even mean to a manager? So the expectations are completely misaligned because there is a lack of good planning, because the coverage scenario is itself informal is not that great, and the managers don't quite know how to understand or extrapolate this. We need to become better at communicating with the management. Missed bugs. So a lot of the time, because of the way the use model is at extremities, people lack good methodologies, misaligned expectations. The end result is we end up missing bugs. This could still be avoided despite all of this if we do proper risk assessment and analysis and go for strategic applications of formal, even if we can't deploy formal throughout all of the IP blocks. So what happens then is you end up having erratas, bugs that actually leak after the design was complete. But even then, when you do find erratas, I think if you can think of deploying formal tactfully, then it will give you a much better return on your investment. So these are areas where users can become better, and this can actually change the game, and this can help realize the vision. So effective methodology training will be a game changer. And how will this methodology make any difference? Because currently the methodologies itself are very much app focused. We need to take a solution view. We need to come out from this app oriented view to an end-to-end solution view. How are we going to solve this next safety critical problem? How are we going to solve this security problem? How are we going to find all of the bugs in a low power design, but also be able to prove aspects of the low power design, if not the entire design? Too much stratified, as I said, we lack the full continuum. Training again is a big hassle. For methodology, there's absolutely nothing. Metrics, as I said, are used only towards the tail end, even for whatever they are, proof core based, cone of influence, mutation based, at the end of the project. I've come across projects where people do unreachable code coverage analysis towards the end. We could do that in the first hour of design bring up. We could find some of your unreachable code, dead code today. There are tools out there who can help do that. Use metrics in an agile way. Be more design oriented, right? Should we be just reading the design to actually find out what the design is meant to do and just copy the design code in our verification code? Is that really verification? No. We need to be requirements oriented. I've come across projects, and I know people still do this, but that's bad habit. That's not going to help. Too much of the verification is micro-architectural, fine detailed signal level. Hey, that's good. We need to do that. We need to find our bugs at the signal level. But let's not lose sight of the big picture. We are today able to verify architectural level properties of some designs and end to end. Bugs, too much fixation with bugs. And I know there is some messaging going around, bugs being the main focal point for formal. You know what? I love finding bugs. I love getting my coverage, but don't lose sight of the fact that we must get our exhaustive proofs whenever we can. All we need is an effective application of a methodology. That would be the game changer. So if I want to sum up my vision for formal, I'm looking for a scalable methodology, combining it with the best tools so that we can get all design verification work carried out by formal whenever it can be for the right reasons, as I said. But now if I go back to what Dijkstra was saying, what he was actually saying when he said programs should be correct was he was hinting at bug hunting. When he said we must prove the correctness of programs, he was actually talking about building exhaustive proofs. When he was saying let's try and think of tailoring our programs to the proof requirements, he was thinking of requirements tracking, requirements-driven verification. When he said this activity will become more and more an activity of mathematical nature, he was actually talking about the act of doing formal would make sure that bugs are avoided in the first place. So actually all of these things that we talk about today can be dated back to Dijkstra's time. What I think he did not mention at the time, and I'm saying that this is the way to change the game for larger scale formal, is to bring coverage right up at the design level. Start running your tools, get your metrics out at the designer bring up time. Continue developing them, continue getting them as you carry out your verification. So coverage for verification, and then use them for sign off. get the whole continuum right. There are coverage tools out here that can get you that. Yes, they're not uniform, as I said, coverage model, but whatever it is, we can use it in a sensible way. So with that, I would like to stop now and thank you for your time, for hearing me out. And if you have questions, if you share my vision, want to be a part of it, contact us at www.axiomise.com and hope to hear back from you. Thank you very much.